All right, hello everyone. Welcome to section 14.2, limit and continuity. So, number one, there's just a little recall here. Remember, we used limit in calculus 1 and 2. We used limit to define continuity. And from there, we can define derivative and integral. Derivative and integral. Okay, so remember the limit in those classes, that is what the limit look like here. So you have a function x, y, and let's say you have something right here, fx. To find the limit at x equal a, so there are only two ways that you can approach. So you can only do the left approach and the right approach. That is it. Only two ways that you can approach here. Well, in this class, we don't have a function that is on the xy plane, but we have a surface. We don't have a curve. In this class, we have surface xy, and this surface has a set of domain on the xy plane. So I'm gonna sketch out the surface here. So let's say that let me see, can look a little ugly, but that is the surface there, surface. So this surface here, it will have a domain. See, the domain is the projection of the surface onto the xy plane. Let's just call it here, right? Yeah, that's the domain. Can be seen as projection of fxy of surface on xy plane. Okay, so now when we have an open circle right here, right? We want to figure out the limit here. What is the limit right here? So in order to figure out that limit, we're gonna have to project that on here. So on here, you're gonna get a point. it has the x coordinate and the y coordinate. See, projection. When we have a point and the domain, it looks like this, that we can approach that point from many ways. You don't have to do the right and the left approach anymore. There are many ways that you can approach the point. So you can do a straight line approach. You can do a curve approach. You can do whatever approach that you like, or you can do a sine, a cosine approach. You see, many ways to approach the point on the domain. For the function, you see, only two ways to approach x equal a. Meaning that in order to show that the limit exists, you got to show that all the ways that you approach, it doesn't matter how many ways, you got to show all of them. The limit has to be the same. Limit does not exist. Do this way, it's easier. Does not exist. D and E. If the limit from any two paths are not the same. Two different paths. In case the limit from all the different paths are the same, then the limit exists. Example. Evaluate. Actually say find the limit if it exists. A limit. Well, because we have a function fxy, so it's going to be xy. Go to, most of the time it's going to be 0, 0. X to the 4 minus y to the 4 over x squared plus y squared. Okay, so what is going on here is that if you just blindly do the substitution, if you do a substitution, so I'm gonna call ds is direct sub here. Yeah, if you blindly do the ds here, you're gonna get 0 over 0. Well, it is an indeterminate form, but because there is a function of two variables, we cannot use the L'Hopital rule. We cannot, right? Make sure you are very clear that there is a function of two variables, not one. Right. Okay, so once you know this much, then that means you have to do something to this. You got to use all the algebra trick that you can to simplify the function. I'm going to do a factor and simplify. Limit x, y go to 0, 0. Well, you can factor this out to x squared plus y squared x squared minus y squared over x squared plus y squared. And then this one, get rid of this. So do the substitution, you're just going to get 0. The limit here is 0. Okay. So here can be limit x, y go to 0, 0. Tangent x squared plus y squared over x squared plus y squared. Same thing here, right? If you do the direct sub, you're just going to get 0 over 0. So we got to do something to this one. Well, we can break it up. Tangent is the every time I write limit, it got to have this. So it take a while here. Sine x squared plus y squared over cosine x squared plus y squared, and then over here x squared plus y squared. Now do a little algebra manipulation, and then you're going to see that you will have a limit x, y go to 0, 0. Sine x squared plus y squared over x squared plus y squared multiply to 1 over cosine x squared plus y squared. Any question, guys? If you guys have question, let me know. Once you do this one, you're just gonna use the limit law. So that is why I have the limit law up here. Use the limit law, and one of them. So it'd be a limit x, y go to 0, 0. Sine x squared plus y squared over x squared plus y squared multiply to limit x, y go to 0, 0. 1 over, oh my God, it's too small here. Cosine, oh my God, it's too small. I'm gonna have to write this in here. X, y go to 0, 0. X squared plus y squared. Okay. So hopefully you remember, right? You can use this one as the limit x go to 0. Sine x over x. That is 1. You can remember this from calculus 1. And then for the other one, it's just do a direct sub here. This one, I'm just going to do a direct sub because cosine of 0 is equal 1. So the denominator is well defined. Okay, we have a 1 multiplied to 1 over cosine 0. So it's just 1. We're gonna be looking at problem in which we cannot simplify using algebra or do any algebra trick that we know. See, limit x, y go to 0, 0. 2xy over x squared plus y squared. As you can see, impossible to simplify. Approach along path x equal y to the 3. Now when you do this, it takes a little bit of time, but it is doable. It's not that bad. What does this mean? It means that limit, right? Well, x equal y to the 3. So that means we have a y to the 3, y go to 0, 0. Make sure you're able to go to 0, 0. Because if you don't, then it is not a good path. Okay, so 2y3 y over y3 square plus y square. Yeah. Well, this is the same as y. Now we can do this thing here. If anything go wrong, right, like you have an indeterminate form, then you can use LH, because we are turning this one into a function of one variable. Yeah. Y to 0. Yeah, sometimes you can get the limit very faster, but then sometimes it's a little slower, you know. Yeah, and then when you plug in 0, you're just going to get 0 to approach a long path. Yeah, just don't beat up yourself, right? It's x equal y here. Right? Begin with something simple. And hopefully you get a different value, right? You want a different value. Okay, so let's see. Limit x equal y, so I'm going to do a y here. Go to 0, 0. 2y y over y square plus y square. Now this, it look good. 2y square over, oh my god, it's 2y square. So that is just 1. Yay! Look at this one here. The limit from two different paths are not the same. Thus D and E. Oh, you must, it's not must, you can pick any path so that x, y can go to 0, 0. Right? There are paths that does not work. Do not work. For example, if you pick x equal y plus 1, right? Then when x equals 0, y does not equal to 0, 0. That is not good though, because you cannot reach the point 0, 0. Then you cannot get to the point 0, 0. It doesn't matter how you try, you cannot get to that point, and that is not a path. Limit x, y go to 0, 0. Yet the only difficult thing about this section is that when you pick the path, you know, sometimes you get the same answer 2 or 3 times and you get a little frustrated. You don't know whether the answer is going to be that one or not. Okay. Because sometimes there's always going to be a path that is going to give you a different limit. And you may miss that out. So, okay, for this one, right? The thing about this problem is that it doesn't matter what path you try, you're gonna get 0. And I'm gonna leave it to you guys to try different pattern. Try different path, we'll get 0. X equal y, right? X equals 0, right? X equal to y square, right? And so on and so forth. Get limit to be 0. Right? Well, when you get limit to be 0, doesn't mean that it's going to automatically equal to 0. You have to prove that it is equal to 0. Right? So once you run our path, next, we need to prove that the limit is equal to 0. Zero. Okay, so how do we do the proof here? Well, there are many different ways to prove, but one of the best way is to use the different coordinate. There is x, y coordinate here. If it doesn't work, use the a different coordinate. You can try polar coordinate, and that is one of the nice way to do. Try polar coordinate. That is x equal r cosine theta, y equal r sine theta, and then x squared plus y squared is r squared, polar coordinate. 0, right? Less than or equal to absolute value. This gives us a lower bound here, x y squared over x squared plus y squared. Right? And then this will, we're going to be using a polar coordinate or cosine theta, r square sine square theta over r square cosine theta plus r square cosine square sine square theta. Yeah. Okay, what's this one? Well, you will see that we have a is the cosine theta sine square theta over down here is just going to be a r square though, because sine square plus cosine square is equal 1. Yeah. And this would be, we know the radius cannot be a negative number, right? So I'm going to do this one first. R. You can actually take out the R here. And then absolute value of cosine theta sine square theta. Okay. Well, cosine square times sine square, the maximum that it can be is going to be 1. Right. So this is going to be less than or equal to R. Limit x, y go to 0, 0 up 0. Right? It's going to be less than or equal to limit x, y go to 0, 0 of absolute value x y square over x square plus y square, and that is less than or equal to because we have the inequality up here. It's bounded by limit. Well, R is go to 0. That is the only way that R can go to 0 is that both x and y go to 0. So R go to 0 of R. So look at this thing here. So we have 0 less than or equal to limit x, y go to 0, 0. X, y square over x square plus y square less than or equal to 0. And then by the Swiss theorem, ta-da, and the property of absolute value, x, y go to 0, 0 of x, y square over x square plus y square equal to 0. Continuity. Definition. A function f is continuous on AB if the limit x, y go to AB, fxy, it has to exactly equal to FAB. Well, we have to have continuity before we can go into derivative and integration. Okay. Here comes an example. Determine the setup points at which f is continuous. Okay. Fxy equal to, usually for continuity we have piecewise function, so I get you to the piecewise function, and then you do use piecewise function when you take differential equation, because sometimes when you do work with electrical circuit, you got to get a system of equation, and then you run into piecewise function and it get pretty complicated. But then you got to be able to deal with these piecewise function. X squared plus xy plus y squared if xy is not equal to 0, 0, 0 if xy is equal to 0, 0. Yeah, so the only thing that we have to be careful here is that it's the point 0, 0. Right? So we want to know whether is the function continuous at 0, 0. So that means we got to find the point 0, 0 and the limit as x, y go to 0, 0. Yeah. Is this limit equal to 0? If it is equal to 0, then it's going to be continuous. But if not, then it won't. Okay. Now, limit x, y go to 0, 0. xy over x squared plus xy plus y squared. Yeah, that's what we need to do here. Is it equal to 0? If it is, then this gonna be continuous at 0, 0. Because what happened here is that you have a surface, right? You have a surface. I'm just gonna do a surface there. I just give you an idea here. So you have a surface right here, right? And then at x y equal to 0 0. So you have this hole right here. Yeah. You don't know whether you can fill that hole with the second piece or not. So that is why you got to determine whether this function is continuous everywhere. But if not, then you're going to have a hole right here. You don't know whether you can fill it out or not. Let's see. What f 0 0 equals 0? Can it? Well, the only way to answer that question is find the limit. And when you do the limit, you got to do different path again. It will take a little practice though, but then eventually you're gonna get used to these path here. I'm gonna say approach along. You can set either x equals 0, y equals 0. Just get one value. The quicker the better. Because if I let x equal to 0 here, then what do we have here? And that's going to be a limit. So 0, y to 0 0. X equal to 0. So it's going to be a 0 times y over 0 square plus 0 times y plus y square. So that's going to be a limit, right? You just have y go to 0, and then you can have a 0. Well, y go to 0 of 0 is going to be 0. Next, you got to figure out something so that the limit is different, hopefully. Approach along. Man, yeah. Usually I try out x equals 0, x equals y square, x equals y to the 3. Yeah. And hopefully it worked. Okay, so x equals y, it's going to be a y times y over y square plus y plus y square. Nice. Y square over 3y square. So this is just a 1 over 3. Ta-da! Oh my God. Limit is D and E. Not the same, so limit is D and E, not equal. And when it is D and E, what does that mean? It means that you cannot fill the hole with f0 0 equal to 0. And so the function is continuous everywhere except for that point.